Good afternoon. And welcome to course that is entitled as Simulation Laboratory course. Even though that this title implies that there is quite a bit of activities in laboratory, that's not exactly the case. And there used to be in this course, there used to be some measurements and there used to be some practical design work that we did in a laboratory. This year is not going to be possible. The reason is obvious. This virus situation, of course, that prevents us to see in a laboratory. This will be 100% online course, exactly the same way than the course that you participated earlier, simulation of a mechatronic machine. So no physical laboratories, no face-to-face meetings. Well, to be honest, maybe there's going to be a face-to-face meetings because instructions that I have received are such that in this third period, which is going to end, I think, end of February, all the lectures should be delivered online. But then the fourth lecture, which is getting started in beginning of March, it's not yet decided. So it's even possible that we can meet in lecture room. I don't know if this is realistic or not, but it will be really awesome because all this communication and everything, uh, no face-to-face meeting. Uh, okay, so there is a question in our stream that maybe it would be a good idea to offer a link for this YouTube streaming in a Moodle site. Okay, I didn't make it because the way the Moodle is constructed is that if I type a message to Moodle, it's just put it in a hold some kind, and it keeps it in a hold for 30 minutes, and then it goes out. And I thought that when I received the message that somebody is unable to know where the stream is, I emailed to you directly without using Moodle. So okay, so seems that you are okay. So what is that we're doing in this course then? Like I said, this is more relaxed course comparing the simulation of mechatronic machine. That means that we actually have quite a bit of flexibilities here. And we can discuss about the subject matters that you're interested in. And I'm going to use this course, like it or not, I'm going to use this course to something that is called career counseling as well. So I'm going to tell my perspective about, what makes sense to do in engineering perspective and in career perspective, and what are the important things to take into consideration. And I'm going to explain a little bit about how is a life in academia, what are the matters that makes great deal of difference in academia, and what are the things you should focus if you decided to stay in academia. And many of you will not stay in academia, but you're going to go to industry. Then we're gonna discuss a little bit about what is the best way to squeeze your weight and kind of find your way to industry. And we looked at in a perspective of more like international industry, and then how is an industry in Finland. Some of you are maybe physically in Finland and you are wondering how is the way that you can find a position in Finnish industry. We're going to discuss about that. But that's actually it is kind of the subject matter that I like a lot. It's not going to take too much of your time. And if it is something that bothers you, we can even take that a little bit off from this technical discussion because we do have quite a bit of technical things to discuss. So what exactly are we discussing in the course then? Well, again, we're going to take a look at the picture that is like schematic representation of how are the dynamic systems, mobile machines, industrial applications, biomechanics, so on and so forth. So we're looking those systems in a way that they consist of several different disciplines. First, an obvious discipline is a mechanism. Mechanism is just to give you an example, is a four-bar mechanism that consists of three moving bodies. So this is an example of mechanism. And a mechanism itself is not going to be a machine. So even if you would like to study that how is this four-bar mechanism, what's going to happen without the actuators is that it's going to find a static equilibrium position that will be something like a little bit like this. And oh yeah, I can see that my face is preventing you to see that. Okay, so this is a four-bar mechanism and a static equilibrium is something like this. and it's not going to move. So there is no dynamics. So to make that move, so we have to have an actuators. And you learn that there is a way to describe hydraulic actuators, and there's another type of actuators as well. So what we're doing in this course is that we wanted to build a picture that covers the machine, how it is as an assembled entity. That's something that is extremely important. So we continue to look up these actuators. We're going to look a little bit about what we can do in this regard. We're going to look how the control system can be embedded, can be accounted in a model. And then we're going to take a look at what this box that is a user, which means obviously that we're looking things in using the real-time simulation. A real-time simulation is the one where a user can be a part of the simulation and part of the analysis. We're also going to take a good look about the working process. That's something we did not look at course that it was in the fall. So again, we're going to take a look at this picture, but a little bit of different perspective than in the fall. Because in the fall, we focus a great deal about the theory of this guy. This time, we're still going to look a little bit about, what is that we can do in terms of mechanical modeling. But the focus this time is in a big picture. Big picture in the sense that we're looking at, what's the relation between the multi-body system dynamics to finite element modeling and other computational methods. So I'm going to make my best effort to give you a good picture. What are all the computational tools that is needed in different product processes? And again, different product processes. So we're not necessarily looking at the product development, but a little bit about how these new digital-based technologies could be used in a marketing, sales, service business, so on and so forth. So big picture. If there is a need to summarize the course, this is going to be a more picture, way more big picture comparing the one that the course one was in fall. Okay, so that's how we're going to go. Then I guess that I did not even mention my name. So those of you that are not familiar with me, my name is Aki Mikkola. Sorry about that. I was maybe I was too excited about starting delivering lectures again, so I forgot my name. I didn't forget my name. I still know what is my name, but I forgot to mention that. So my name is Aki, and please call me Aki. And the way you can contact me is that you can send me an email. By the way, I'm not sure if this email address works at the moment. At least what works is my first name, which is Aki, dot my last name, Mikkola, Mikkola, at lut.fi. For sure that works. And I'm here together with Suraj. So Suraj, you good to know Suraj in fall class, and he is again with you. So he is my teammate. Suraj got really good evaluation from the fall course. So many of you spoke really highly about how pleasant guy is Suraj and how he helped you to do things. And I was so happy that he's willing to cooperate with me again, which is nice. So I'm thinking this is going to be something pleasant, something enjoyable to you. So it's me and Suraj. And the best way, if you wanted to have, there's something you wanted to discuss with me, you can send me an email. And of course, as you noticed, right after today's lecture at 1:45, there's going to be a question and answer session in Teams. That's the same technique that I used in a fall. So what we're going to do today is that we're going to cover the ground rules, basic rules, the content of the course, and then we're going to start discussing a little bit about the technical matters, and that's it. And then because each lecture should be 45 minutes, and I'm not planning to have a break today, so we're closing roughly at 1:45, and then you will have an opportunity to discuss with me in Teams. Yeah, that's reason for that is that this YouTube streaming, which I kind of am a bit advocate of YouTube streaming. The communication is not so great. Of course, the interaction, you can use this chat window, but other than that, there's no way to hear you. There's no way to have a proper conversation with you. So to have a proper conversation, that's why we're gonna have the team session. Right. So what's gonna happen in this course? What is an objective of this course? Why it makes sense to participate this course? This course, which I earlier mentioned, that is my favorite. I mean, that is, if you make a list of the good courses in LUT, this is what I like the most. Why? Because this is this topic that I like a lot about the simulation, but not as theoretical as the one that was in a fall. Of course, we are struggling with the certain theoretical difficulties. I mean, that some of the things that I'm about to explain you are, frankly speaking, they are painful and they are not so easy to understand. Some of them are like, for sure you're gonna develop the headache when you listen to me. But again, we're gonna focus on the big picture, what it means, what those means for us, and how is that we can use those tools in different product processes. So, what exactly then? What is that we're doing? Well, the first thing we do is that we're gonna extend our knowledge from the fall course, which was focused on planar case, to spatial cases. So we're gonna move from 2D to 3D. So what's that? Well, some people are saying that it's just adding the one more dimension. It is just adding the one more dimension, but adding this one more dimension comes with the major headache. It's gonna be, I mean, that if you need to compare like how is a level of difficulty in a 2D case versus 3D case. 3D is in a different planet, a different wall at least. And it's what it is that's simply because the rotations in three-dimensional space are not simple to understand. And that's what we're gonna discuss today. We will get started from that, and then using a little bit about this subject matter. We're gonna discuss a little bit about that subject matter next Wednesday as well. So now I'm back. Yeah. So what happened was that my phone was ringing. So what I need to do, I need to make a little bit of tuning to my settings here, such that if somebody's calling me, is not coming to this headset. Let's see, how can I do like this? Okay, now it should be okay. Sorry about that. So there was a break for yeah 15 minutes or so. That's simply because this guy phone. Now it's okay, and again I'm trying to do my best to develop the quality to be something that is pleasant for you. And in that regard, by the way, the one thing that I'm still middle of, still is underway, is this camera system. Camera, I'm not completely happy about that, and I really wanted to start using this guy here, which is something that is quality-wise should be way much better. So it's a GoPro, this guy. But cables are still not purchased, so hopefully they are with me on next Wednesday. Okay, so back to business. Back to business. Sorry that I'm explaining things in a little bit slowly, but to be honest, it's just because I've been missing a lecture a little bit, not a little bit, quite a bit, because it's enjoyable time for me because I can focus on explaining things to you, and that only. There's no disturbances here, so that's what makes me happy. So what else are we gonna learn? So we're gonna learn about 3D, not details. I'm not gonna expecting you to know everything, but I would like you to know why 3D is computationally difficult. And if you know that, that's all I'm expecting you to know. And we're gonna put quite a bit of effort to modeling of flexible bodies. That's interesting. Not necessarily because you know you need to model deformable bodies in multi-body system, but it's interesting because that combines your knowledge from several other courses. So this combines the knowledge from vibration, finite element modeling. If you're not familiar with the finite element modeling, that's okay. If you're not familiar with the vibration, that's okay too. But there are many things that kind of are needed as a foundation to be able to model flexible bodies. And that's why honestly, I like the subject matter quite a bit. And then hopefully you too. And it helps you to kind of see the big picture, like what is the relation between different courses, like course that is delivered by, or was delivered, I think, was delivered by Jussi Sopanen, and then courses that are touching the finite element modeling and so on and so forth. That's something that I feel that is interesting. I'm even planning to explain a little bit about what is the kind of like the theory behind the finite element modeling. And why is that? That's simply because every now and then I hear that there is a serious misunderstanding about what the finite element modeling is about. And I would like to give my understanding, like my expression about finite element modeling to you. And another reason is that, you know, some years back, we got the message from student union that students are looking for more information about the studies and research studies conducted in LUT University. Many of the papers we've been producing in my team are related to finite element modeling, nonlinear finite element modeling in framework of multi-body system dynamics. So that's one more reason to explain the flexible bodies to you. And of course, not just the theory, but the understanding what is a relation between the simulation models and reality. And we're going to discuss about that simulation disease, which is this serious medical condition that you don't do thinking anymore, but you just computing everything. How you can get rid of that. So what kind of medication is needed to get rid of that? We discussed that and many other things. And learn critical thinking against computer simulation. Against, yeah, you heard it right. So I wanted you to kind of think about if this makes sense or not. And that's too bad that we cannot have face-to-face communication, because that would be outstanding to have good discussion with you. And then other methods, we're going to look a little bit about other computational methods, those theories, looking a little bit about how is their limitation, advantages, and so on and so forth. So I tried to build the picture, like where you can use different methods. And that's important, because maybe you're never going to use those methods by yourself, but you may hold a very important big shot position in the company, which is purchasing these services from consulting companies. And when you're purchasing these services from consulting companies, it's good to have an understanding what's possible and what's not possible. That's what we're going to discuss. And then applications. We're going to look a little bit about the vehicle modeling, contact modeling, finite element, so on and so forth. A lot of application, even product lifecycle management and that kind of stuff. This course is like half and half. Half of the course is related to these theoretical lectures and written exam associated to theoretical lectures. Another half is related to simulation work. And the simulation work is this kind of crane that you are modeling by using a student-specific initial values, and it's a hydraulically driven crane where this lift arm here is modeled as a flexible body. The details will be explained by Suraj, but this is a work that modeling-wise, I'm expecting you can do it that easily within a week. But then you need to put things in a writing, so you need to put together a report. And that's another thing that I would like to teach you, because I would like to discuss about the thesis work with you. And what are the good things you should do whenever you're putting the writing your master thesis. And some tricks, some hints do this, don't do that kind of stuff. But that's going to be a bit later. So reporting as well. Reporting is a work, or is a kind of like a talent that you learn by doing. So there is no other way. This is going to be one of the first things that you practicing yourself towards master thesis work. Okay, lectures. So today we will get started from the introduction. Soon I will speed up, so it's not going to be this slow all the time. And then we will discuss about three-dimensional multibody dynamics. And we continue on that topic next week, Wednesday, and then we're moving on to flexible bodies. And we're looking a little bit about the safe functions, accuracy of finite element model, equation of motion, and so on and so forth. And then eigenvalue analysis. This is the link to vibration. Model reduction technique is something that maybe you're already familiar with, and that may be the case if you've been in Jussi Sopanen's class. And moving forward, next semester we're going to have a bunch of visiting lectures. So there's a visiting lecture in a vehicle modeling, visiting lecture in a biomechanics, visiting lecture in a gamification. And we're also going to look a little bit about what's the link to steel structures and how the multibody simulation can be used as a part of the fatigue analysis. And then shortly about how is a large deformations and contact modeling, which take you really close to game technology. Contacts definitely are needed in many of the games. How to make those happen, we're going to discuss those in next period after the midterm exam. By the way, one thing here. So midterm exam is mentioned here, but I will give you more information about how is that you can complete the course. This is something that we must have a common understanding before we can move on. Okay, so these are the things that are related to tutorials. This second part. So there's a half and half, one half related to lectures, another half related to simulation assignment. This is details related to simulation assignments. There are mid-reports that we're expecting you to start put things in a writing. This is a skill we wanted to teach you in a very, well, in this course, such that whatever you do something, you put things in a writing and you kind of practicing to make a report, because unreported work is unfinished work. So you can close the case once the report is ready. Prior to that, you cannot. Okay, but we're gonna deal with this. There is things related to three-dimensional mechanics, hydraulics, and then finally flexible bodies comes into play. And these are when the mid-reports are due. And next period is gonna be verification, control algorithm, reporting, and the final report is then here. Okay, grading. Okay, now if you've been a bit tired and not following me carefully, you need to wake up and you need to listen to me carefully. So this tells you what are the mandatory components to pass this course. And you must know the mandatory components. This is your responsibility. So if you come later and say, well, I wasn't aware of this thing, I cannot really help. So you need to be aware of what I'm expecting you to do. Okay, so 2 mandatory items. Accepted simulation work. That's number 1. So it needs to be made in a way that when Surat is creating your simulation work, he have to feel that this is acceptably made. Acceptably made is not the clear-cut case. There is some freedom for, we can be flexible in this regard. There is a possibility of negotiation and so on, but we need to see an effort here. And the work actually is not so bad at all. So it's something that is not going to be bad. And if you follow these midterm reports, you're going to be okay. Second mandatory item here is accepted written examination or 2 mid-examination. 2 mid-examination is actually a way to go. Again, how it goes? Well, shortly. When later today we're moving on to technical matters. In the very beginning of each technical matter, I'm going to give you the possible questions in that subject matter. So that, of course, this is a material that will be available in a Moodle database. So you can take a look at those questions afterwards, and then make sure that you're understanding, or not understanding, but you're able to answer all those questions. So what I'm expecting you to learn, that is mentioned in the very beginning. So first comes subject, what I'm expecting you to know from the subject, and then explanation. And then maybe I should maybe even make one more improvement for that, and that will be of course, the fact that once we covered with the topic, then we look at the questions and like how is that you should answer those questions. Okay, so what that tells you, it tells that you stay tuned, you follow the lectures, and that's it. That's it. So it's going to be very easy. So it's going to be very enjoyable ride for you. So not bad at all. Okay, then final grade. How that is computed? Is computed in such the way the simulation work plus written examination is divided by 2. So it's an average from these 2 items. So let's say that hypothetically you score 3 from the simulation work, 4 from written exam. That's going to be 3.5, and it's going to be always rounded up, so it's going to be 4. And then in-class quizzes is something that those of you that are following my lectures, you know what's the deal with that. You could get additional 0.5 points. Okay, so the 4 comes out from this part of the equation. So then you are doing well with the in-class quizzes, and you are able to get additional 0.5 points. So that's going to be 4.5. Finally, your final grade is 5. So that tells you one possible way you can score 5. But remember that the maximum grade is 5. So make sure you're following something that is called principle of minimum energy. Don't overdo the course, because by overdoing you can get 5 from written exam, 5 from simulation work, 0.5 from in-class quizzes. That would mean that you will get 6 from the course, which I'm unable to give it to you. So make sure that this would be the optimal way to do it. Maybe it's a little risky way if you really wanted to score the 5 out of 5 from this course, but we'll see. So lectures always on Wednesday. So we have a YouTube channel, which you probably are already familiar with. In that YouTube channel, there are lectures from last year course, which touching the more or less same subject matter. Last year, though, it was different than this year, because in the beginning, everything was made in a lecture room, and then somewhere in the middle, everything was made online. So you can take a look at that. But this year lectures is the one that I'm expecting you to follow. So if you are running out of the time, you're busy, you're not really interested in the subject matter, that's okay, because you can just focus on then this year lectures. Okay. Tutorials, the one that Suraj is responsible of, those will be on Fridays. I know that in somewhere in our website it was mentioned that there is 2 tutorial groups, one on Thursday, another one on Friday. The one on Thursday will not take a place. And the reason behind is that we have a total of 41 students in a class. So, and again, because everything is online, so we're expecting to be able to handle that much students in one tutorial class. Suraj will email more information. But again, no mandatory participation in lectures or tutorials. So if you feel that tutorials, I need to move on a little bit so you can see it. So if you feel that tutorials are not for you, lectures are boring, fine. Don't come to lectures, don't follow the recordings. Just read the material. There is this handouts available in a Moodle site, and you will be good. If I can give you a recommendation, don't do that. Because, the still things we're going to explain, or what I'm about to explain you, are not so simple. The easiest minimum energy principle would be to follow the lectures. Then you will see all the questions that I'm asking, and that's it. By the way, in just before the midterm exam, there is a Teams telemeeting, and a Teams telemeeting we're gonna conduct a voting action, and in that voting action you can select the one question that for sure will be in in an exam paper, and one question that for sure will not be in the exam paper. Then there is a question like, what about the tutorials? Are those recorded? I'm not 100% sure about that. I think of the style that Suras is planning to do is that he's gonna make those YouTube videos, which like the case that was in a previous time in a fall class. So those definitely are recorded. Then this hands-on guidance. I'm not 100% sure. To be honest, I did not discuss this with Suraj. My mistake. Okay, but the more information will be available momentarily. Maybe Suraj is following this streaming, so he can get back to you soon. Or maybe if Suraj is following, maybe you can type the answer for that in live chat. I cannot see who are the people that are following. I only see the numbers, but I don't see who is, if the Suraj is here or not. Looks that he's not here. Oh, okay. So Suraj is here, and he's saying that. So are you answering that tutorials will be recorded? Yes. Great. In-class quizzes. So you know the business. So we have a total of 25 points, and then how to enter your answers is that you just install the Socrative app, or you're using, browser, and you log in yourself to Socrative website, and you log into Room, which is called LUT, and LUT Room is waiting for you. You may try to log in yourself to this website already this time, because last time we were experiencing some technical difficulties, which was a little bit unclear to me, like where those came eventually. And the way you can log in, that you need to use your student ID number, because otherwise there's no way to know who is who. Okay, how is this created? So if you're scoring 0 to 13 points, that's gonna be waste of time and effort. You gain nothing. You're gonna get nothing out of the in-class quizzes. But if you're scoring 14 to maximum points, that's when I'm gonna give you this 0.5 points. So look at this. So again, I'm not expecting you to be perfect. Okay is enough. And okay this time means that if you're scoring 14 out of 25, you get this extra 0.5 points. Now, another criticism that I got from fall scores was related to this delay of the grading. I will make my best effort to grade everything in timely manner, such that if there's a lecture today, you can get the grading same week. Hopefully it works. Still don't have a automatic system, fully automatic system to make it happen. So also note that we're kind of forcing you to submit mid-reports in timely manner. How is that we can forcing you to do so? Well, it goes such the way that there are certain deadlines, and if you submit it after the deadline, we're going to take you 0.5 points off automatically. It's a little rough, but it is what it is. And remember, there were 3 mid-reports, so if you miss them all, excuse me, so it's going to be 0.5 multiplied by 3, 1.5, minus 1.5. So if you do good in your simulation assignment, you get 4. So that's going to be minus 1.5. 2.5, which is still rounded to 3, but it makes an effect. So make sure that you do everything timely matter. Respect the deadlines. That is important. Here are the deadlines. How it goes in details, you're going to learn that from Suraj. Look at that. So there was a connection problem. I see that my OBS was complaining that the connection was broken for several seconds. I'm disappointed because I thought that the investing to this mesh network was a good decision. But seems that is not that reliable. Okay, previous knowledge. Now then we're ready to move on to introduction. So I'm expecting you to be able to, that if you have made a simulation of a mechatronic machine acceptably, and that would be really great. And if you've been somehow following the course, that would be really great. If not, if you have not participated in this course is still doable. It's going to be a bit challenging, but it's still doable. But definitely what I'm recommending is that this would be something that gives you good background, beautiful background to pass this course with not too much of an effort. If not, then you need an effort. Then then you need a considerable amount of effort. It's still doable, but something that can make your life less pleasant. Let's put it this way. Okay, what I'm expecting you to read, there's a handouts. Take a look at the handouts. It's still not 100% completed. I'm putting quite a bit of effort to try to make a kind of a book out of this lecture material, but this being a project that I've been on already like 15 years, maybe even longer than that. So don't expect that to be ready anytime soon. So, but I'm gonna put in the material as soon as it's ready to your knowledge and for your use, and it's gonna be via Moodle. There's of course gonna be these PowerPoint presentations, which will be enough. So if you're just following the PowerPoints, I don't think that you need much more than that. Then there is Ahmet Shabana's book, which is a great book. I don't know if I mentioned this to you earlier, but I made my postdoctoral period under the supervision of Ahmet Shabana in University of Illinois at Chicago in UIC. And then many of the things, that this is a reason that many of my explanations, many of my notations and so on and so forth are based on are exactly the same notation that Ahmet Shabana is using. So in that perspective, it should be okay, somewhat easy to understand this book. So if you wanted to take a look, how is this book entitled Dynamics of Multibody System, you can borrow the one in University Library. This mentioned that chapters 5 and 6, but actually there are more that is, pretty much all the book. Book itself is like this thick. That's a lot to learn, and I don't expecting you to borrow it. But if you wanted to learn more, yeah, that will be the one way to make it happen. Okay. Introduction. Final introduction. So seems that I'm going to use the first 45 minutes for this ground rules, general matters, and introduction. And I see that when I look in my YouTube studio, my picture is a bit blurred for the reason that I don't know, but OBS looks okay. And I see that there's no complaint, so I'm expecting everything to be okay. Introduction. What I will learn in this course. So what are the things you will learn? And let's take a look. The big picture, what I would like you to learn. What the big picture means. It means that typically in today's analysis, in different product processes, we are looking at the multidisciplinary analysis where there are several different things that are combined together. This is something that is called coupled simulation, which by the way is a first question that is possibly in a written exam. So the coupled simulation means that we're combining different disciplines to one simulation model. And it could be the case that we're combining the mechanical model that is initially made in CAD software of some kind with finite element model, which is the one that is shown here. So it looked that there's a structure where there's like a fishing net top of the structure. That's a good example about how the finite element model look like. Those two things are combined. And those are combined with control scheme, model of actuators, and so on and so forth. So we try to see, what is the relation between these two methods? Multi-body system dynamics, this one, finite element modeling, hydraulics, control algorithms, CAD software. We actually looking at how this relation is. So how you can convert your CAD model to be a finite element model, contact modeling, and many, many others. So this is what we wanted to learn. And this coupled simulation that can be, in practice, accomplished in a way that everything is put mathematically to one big set of equations. That's one way to make it happen. Or you can use something that is called co-simulation. And in a co-simulation, there are different kind of solvers in different software, and they're solving that one particular discipline. And then they are sharing information with other softwares. And this is something that makes it possible to analyze these multidisciplinary systems. And this is it's important to understand that we're doing this because current machines are something that there are a number of different disciplines combined. If you think about this famous thing about mechatronics, it refers to the fact that there's a machine where there's a mechanics and electronics, some kind of electronics. Okay, so what it means in today's products? It means that practically every single product is a mechatronic product because mechanics without electronics is not very common. Maybe the hammer is the one which is without electronics, but all others are coming with the electronics. And they typically, when you look at more advanced products, mobile machines and so on and so forth, there are a number of different disciplines that are all put together. What matters is obviously how the system as an assembled entity performs. That's what we wanted to learn here. Okay, still my picture look a little bit blurred in my YouTube studio, but OBS looks okay. Then we're looking at this mechanical flexibility. We're looking at how this small deformation can be modeled by using very general systematic approach, which is easy to use. That's what I'm about to explain it to you. And again, it combines the vibration, finite element modeling, model reduction, many different things which are good to know. Even if you're not or never going to use them, if you're never going to model flexible bodies in your career. And then we're going to look, okay, what it means if we wanted to model something that experience a large deformation like the belt that is showing here, this belt here. Okay, my phone is ringing again, but I can see that is no longer bothering my headset. So we are good. Then failure. How is that we can make an extension from multi-body modeling to analysis of fatigues and other failures? That's something that is quite interesting too. And again, gives you a little bit of different point of view. Like if you just look at how is a dynamic performance, of course, it's important to know, like, are they well made in such a way that they can, they performance is good enough and they stands like that good performance long enough. So one of the things that typically are problem in many of the mobile machines is fatigue, and fatigue of welded structure particularly. How is it we can analyze those by using the multi-body system dynamics? There's one short lecture in that subject matter. Then contact modeling, we're going to look a little bit about different contacts, how those can be described, what are the methods used in CAME technology. By the way, that's what we're going to look, and also in a multi-body system dynamics. This is a bearing model, and as you can see that the bearing force, or the force that is imposed to this boundary, is actually fluctuating, and that's simply because the balls can have a configuration like this and configuration like this. Oh, sorry about that. And the force is traveling here to here, and of course you understand that this is introducing the different condition than this one. And this is a kind of what we can analyze by using the contact modeling and many other things. By the way, if you want to see something like what are the latest developments in contact modeling and something that is called many-body dynamics. Many-body dynamics refers to system with really many bodies. I'm not sure where exactly is the limit between the multi-body and many-body, but I'm thinking like if you have a more than, oh, you cannot see the video. Really? So if you want to see what is how is a many-body, which is a system consists of more than 1 million bodies, go ahead and take a look at this website. This is something that is interesting. Oh yeah. Sorry about that. My face. Yeah, okay. Yeah. Sorry about that. So let me take this off. Let me try to move this. Yeah, there is of course a high temptation that I wanted to make a drawing to place which is empty in a slide, and that's exactly where my head is located. Sorry. So I was about to tell that the support condition is different when the balls are like this, and the force is traveling between the balls, or where the force is traveling through the one ball. Though that's where the fluctuation is coming from. So if you look carefully, reaction force is not standing constant, but it's fluctuating, and this fluctuation is because this boundary condition is changing. Yeah, thank you. Okay, so we done. So we done with that introduction, and of course it will be nice to say, okay, now you can ask a question, but this is a little bit complicated. As I mentioned earlier, this communication is not fluent in YouTube. So what I will do is that I'm going to take a look at the live chat every now and then. If there's any questions that you would like to ask now, go ahead and type your question to live chat. And seems that we can move on. And the first thing that I would like to do is that let's take a look. How is this three-dimensional spatial multi-body dynamics? Three-dimensional multi-body dynamics. In this area, these are, let me think how many there, 7 sub-items that I'm about to introduce to you. So we can get started from the introduction. Then we come back, we look at the description of particles. So somebody was asking if there is a rotational particle in this course. Yes, it is. So here it comes. It's the second topic right after the introduction. And then we're going to look something that you are already familiar with. So we're looking at Euler angles and then Rodriguez equations, not equations, and Euler parameters. That is very much related to Rodriguez equations. So Rodriguez equation and Euler parameters are like brothers. So they are more than brothers. They are like twins. Euler angles is, even though that the name implies that it's somehow related to Euler parameters, that's not, there's no relation. I mean, they are not relatives. Euler angles and Euler parameters are not relatives. They're completely different concepts. And then we sort of discuss about rotational properties of rotation matrix and robot kinematics. Robot kinematics, by the way, is a very interesting topic too. Here, this is what I could ask in written exam. And here's the deal. All the questions that you will find in the written exam are the one that I'm listing here in my explanation. So I'm limit myself to these questions. So I cannot ask anything out of the one that is already mentioned. So if I'm going to ask something like, okay, what about, I don't know, space satellite? I cannot because it have to be out of these lists. So it's exactly these questions, word to word, what I'm about to ask in midterm exam. So if I could ask, for example, what the coupled simulation means. Coupled simulation, you know what it means. It means that you're combining different disciplines to one entity. And you can do that in a monolithic way, which means that you put everything to one big set of equations, which you're solving by using one time integration scheme. Or you can use multiple integrators and then sending information back and forth between the different integrators. Those are the, generally speaking, those are the possibilities how you can make this coupled simulation. But coupled means that you're coupling different disciplines to one model. That's what it is. Okay. And the rest of the question you can see it here. And now it goes such the way that once we moving on to details, I'm always telling that now next I'm about to explain the things that are related to these questions. The first set of the questions is like, what kind of system can be analyzed using the multibody system dynamics? And what the coupled simulation means, which we already addressed, so no need to go there. And why rotation, well, I can see that there is a spelling mistake, why rotations are more difficult in spatial than in a planetary case. So that I need to fix that. And how the exams are organized, that's a question from chat window. Not sure yet. They used to be paper exams, but I'm expecting to get more information from LUT administration. So I cannot answer that question today. Hopefully I'm able to answer that question next Wednesday. Well, or let's say well before the exam will take place. Okay. You sure with the rules? So you know the rules, so I'm recommending you to participate the midterm exams. Look at the questions. And I'm only asking these questions, nothing else. Of course, not all these questions. I'm going to select, so I'm going to use a lottery some kind. So I'm going to select if some of the questions which I'm asking from you. So exam is not going to be similar than in the last semester. And the reason is that last time it was automated, such that there was a question bank. And you need all correct answers for all the questions. This time it's going to be manual checking. So I'm going to check the exam. So I'm going to select the certain questions, going to put it in a paper, or if not in a paper, then I guess Moodle, not sure. And then you type your answers by handwriting or a computer, and then I'm reading and I give my grading to you. That's how it goes. Okay, multibody. Let me see if there's any other questions. Seems not. Okay, this is a kind of refreshing your mind. What is the multibody system dynamics? And look at this. So the first question is that what kind of system can be analyzed using multibody system dynamics? So to answer that question, you need to know what is a multibody system. And here is an explanation for you. So the multibody system is a system that consists of multiple bodies. That's not enough for the definition, because the multibody system is a system where these bodies are connected together via mechanical joints. Remember in fall we look at this not 4-bar mechanism, but crankshaft mechanism, like this. We concluded that the crankshaft mechanism is something that consists of 1, 2, 3 bodies, and these 3 bodies are connected together via joints, constraints. Mathematically, those joints will be expressed in terms of constraint equations. There is a revolute joint that connects this body to ground, There is a revolute joint that connects these two bodies, and there is a revolute joint that connects the connection rod to piston, and the piston is connected to crown via translational joint. So this is a multi-body system. And that's the definition of multi-body system. Anything that is in this category can be analyzed by using multi-body system dynamics. That covers robotics, mechanisms, biomechanics, vehicles, aerospace applications, and many, many others. So you can just imagine like how many things can be described mathematically by bodies and constraints. That body of application is huge. That is very big. Now, in multi-body system dynamics, we do not make any assumption regarding the magnitude of rotation. That's important. Why it is important? That's simply important because if we are not limiting the rotation, it means that the kinematic description will be nonlinear. And it will be nonlinear because it's going to have, in our case, it will have these trigonometric functions, sine and cosine. And those are nonlinear functions. And if we have a nonlinear equation of motion, generally speaking, there is no analytical solution available. How is that you can solve this equation of motion then? Well, you can solve those equations of motion by creating the equation of motion and solving those by using a time integration scheme, numerical time integration scheme. That's what's possible. It's also possible to look at those in a frequency, linearize it and look at the frequency content. And that's something, and again, that I'm repeating over and over again, like what is a linear dynamics, nonlinear dynamics. So we're looking these differences really, really many times in this course. Okay, building the equation of motion in multibody, using the multibody dynamics, forget about big brains. Don't use your big brains, you just use the steps that was introduced last semester. You follow those steps, you're gonna get automatically the equation of motion. But as soon as you start thinking, okay, I'm so clever, I can find a relation about this and that, that's where the thing's gonna go south. Don't do it. Don't do it. Okay, so mentioned here, like multi-body system dynamics can be applied to robotics, mechanisms, vehicles, many, many different kind of machines. That's answering the first question, which was again, what kind of system can be analyzed using the multi-body system dynamics? Okay, hopefully you're happy with that. So let's move on to real three-dimensional spatial case. Here it is mentioned that it's more cumbersome. I mean, modeling kinematics of three-dimensional body, like this guy here, is way more complicated than when using a planar case. So what is the difference between this picture and the picture we looked at the last semester? Well, last semester we always look at the case where there was a, I guess here, x-axis, y-axis. That was where we limited ourselves. This time I have third axis here, which is a z-axis. Okay, what makes this so difficult? I'm going to explain it to you right now, and then I will repeat the explanation 200,000 times in this course, because when I'm about to explain to you, it's going to be very, very painful. And it's not about your internet connection. This is just something that is hard to understand. Okay. So in three-dimensional case, it's clear that the body can rotate in three different ways. So the three different rotations that can take place. And those three different rotations, well, we can express those three different rotations by using Euler angles, Euler parameters, Rodriguez equation, and so forth, and many different ways. Those rotations can be expressed as a vector theta. And this vector theta, this is the one that consists of, if we're speaking about Euler angles, I think that it was a, I don't remember what this is called, phi, I think, psi. I'm not 100% sure about that. This is definitely theta, and this was, forget about that, the names. These three parameters were used to describe the rotations. Okay. Now, if you're using some other method, you're going to have a different set of parameters. But the difficulty is this. When you look at the angular velocity of that body in terms of global coordinate axis, like these guys, or body reference coordinate axis, okay, then these two guys, this guy and angular velocities, excuse me, these angular parameters, time integration of the angular parameters are not same. And I'm sure you're like, what? How come? Like, of course they are same. Well, of course they are not same. And that's what makes things difficult, simply speaking. Okay, what it means for us and how we can solve the problem. Well, we can solve the problem by using something that maps these relations. And we're going to get back to this, like how it is mapped, but we're going to, shortly speaking, we're going to use something that is called as a G matrix. Now, if you heard me like this, and you understood nothing, that's okay. That's okay, because I'm not expecting you to understand the difficulty based on that brief explanation. This is just for your knowledge, what makes this so difficult. Okay, so, and now I got the information that this guy here is called phi. This is theta, I knew it, so I got the point, so I scored 1 out of 3. And this is psi. I think that I said correctly that, did I? I think that I said. So I give myself 2 out of 3, which is following the principle of minimum energy. It's enough, so it's okay. Okay, great. So again, we're gonna get back to this why it is difficult. This three-dimensional modeling, three-dimensional kinematics versus planar kinematics. We're gonna repeat this many times. So we're gonna look at this in a different point of view, and that's why I'm expecting you to finally to understand this. Okay. Now, just a few general observations here. In three-dimensional space, another thing that makes a big difference is that the order of rotation is something that you cannot change. You can make an experiment by yourself. You can take a matchbox or any rectangular shaped object like cell phone, and you can do 2 rotations. First around, well, if you put the coordinate system here, first around, say, x-axis like this, and then around y-axis like this. You do the same but different order, and you will find out the phone will be in a different orientation. So you cannot change the order of rotation in three-dimensional space. That's okay. That's not going to make a major difficulty for us. But what does is the fact that is mentioned here. So he's mentioned here the same thing that I just explained to you. The angular velocity is not the same as time derivative of angular generalized coordinates. Yeah, no one can understand that statement. It's so unclear statement. But basically, the one that I mentioned, we need to get this G matrix to map these two things together. What's the deal of the G matrix? Where the heck G matrix is coming from, and who invented that? That I will explain you a bit later. Okay, now another question that was mentioned in this introduction was this couple simulation. Here's the solution for couple simulation one more time, just to make sure that you are able to answer. That you're able to address that possible question correctly in written exam. So it means that you're putting different disciplines together. You're making a model where everything is accounted. Different disciplines are accounted. So that's what the coupled simulation means. Okay, that's about it. Description of particle in three-dimensional space. That's going to be simple. Very simple. Maybe this is even not necessary to repeat it. I need to turn a little bit that you can see my writing here. Now, we're going to use exactly same idea than in planar case. So we're going to describe a particle by using a body reference coordinate system. Now, here is the deal again. Particle is something that you cannot find in a real life. So there's no such thing like particle, because the particle is really tiny. So it's so small that you cannot even see it. So extremely small, something that you cannot go and purchase, and you don't know what color it is, and and if it is capable to talk to you. Nothing like that. It's just a mathematical quantity of something that is very small, so small that its rotation makes no difference. Because if it is just a tiny, tiny dot, how you can tell what is its rotation? You cannot. You cannot because it's so small. Okay, that's what the particle is. And you keep on adding these tiny, tiny things called particles. You get the body, and you get another body. You will have a multi-body system. So particle. So let me make this line to you again. So particle, uh, spelling mistake, particle, body, multi-body. But this is where we need to get started. This guy, particle, do not have a rotational degrees of freedom. Body, which consists of number of particles that actually have a rotational degrees of freedom. Multi-body system, well, there is a multiple rotational degrees of freedom because of the multiple bodies. But the first thing, you need to understand the difference between the particle and the body. And the difference, shortly speaking, is the fact that particle is a tiny, tiny thing which makes the body, but it's so tiny that it do not have a rotational degrees of freedom. That's why when I'm expressing the position of a particle in any reference coordinate system, in any coordinate system, I can do that by using a vector which is just pinpointing its location, because that's enough. I don't need to know about anything else. I don't need to know about the rotations or anything like that, because I just need to know its location, and that's it. Okay. No, I'm not going to spend too much time in this slide because this is the stuff that you're already familiar with. So how can I make it happen in using this body reference coordinate system? Well, it goes such the way that I attach the assisting coordinate system, which is called body reference coordinate system, to a body. And this is attached, so it cannot move with respect to body. So this guy cannot move with respect to body. So if the body translate, body reference coordinate system will do the exactly same thing. If the body rotates, the body reference coordinate system will rotate as well because it attached. It's like welded. It is nailed to it, so it cannot move. Okay. Now what we're going to do then is that with respect to this body reference coordinate system, we can easily describe every single particle because there is so many particles, millions and millions of particles that makes this body by using a constant vector u bar. And constant vector because we are assuming this body to be rigid. If it is rigid, then this vector u bar is constant. If we're speaking about deformable bodies, then actually the big difference is that the vector u bar is no longer constant, but it will consist of two components where the one is telling its original location, another one is telling how it is moving with respect to time. But we will get back to that a bit later. Okay, so vector u bar is the one that scans within the boundaries of the body and tells where all these millions of particles are located. Now, because this vector u bar is described in body reference coordinate system, it needs to be converted to be expressed in global coordinate system. Because in dynamics, everything is measured in reference coordinate system, which often is a global coordinate system. How we can make it happen? Well, we can make it happen this by using this numerical matrix called rotation matrix. So it's going to be 3x3 matrix in spatial case always, even if we use 4 parameters to describe it. Still, it's going to have mathematically 3 rows and 3 columns. All right. And then we also need to take translation of body reference coordinate system into account, and that's going to be accounted by vector r. So vector r is a vector consists of 3 components, which are projection in global x, y, and z direction. And then we have this rotation matrix, how to express that. That's what we're going to take a look at next. And then we have a vector u bar that is with respect to body reference coordinate system and consists of 3 components. with respect to body X, body Y, and body Z coordinate axis. That's how it goes. All right, today we're going to focus on this guy, rotation matrix. And how is that we can describe that? First, by Euler angles. Let me see what time it is. I can see that I have 20 minutes. 20 minutes. How come? Is it like I'm extremely slow? And I think the answer is yes, extremely slow. Okay, so this is Euler angles is something that you are already familiar with. So I'm gonna shortly introduce that to you, and then hopefully I kind of like to open the topic of Rodriguez equation to you, because even if we're unable to complete it today, this is going to be something that kind of is already in your brains. And the next time, next Wednesday, when I get back to this topic, you get the better understanding about what is a deal with the Rodriguez equation. But prior to that, Euler angles. Questions about Euler angles are here. Two different questions. Explain the concept of Euler angles, which is like, what is a deal with the Euler angles? You know, how they can be formed, what the parameters are describing, so on and so forth. And another detail related to this is Kimball locking. Kimball locking, which takes a little while to explain it to you, but it is related to this singularity that is always the case when you're having the three rotational parameters. That is by the way, that we are not going to use three rotational parameters well after these Euler angles in this course, because the Rodriguez equation and Euler parameters are using four parameters. Four. 1, 2, 3, 4. Four parameters to describe the body rotation. And this is conceptually like, what is it? Is it means that is that the same that the body can rotate in 4 different ways? No, that's not the same, because these four parameters are not independent. They are dependent, meaning that we have four parameters plus one constraint. One constraint eliminates the possibilities how these parameters can move, meaning that only 3 is left. And when 3 is left, is meaning that the body can rotate in 3 different ways. Why we do this? We do it because all the methods that are using 3 parameters are suffering from mathematical difficulties, such like Kimball locking. Okay, there are some good stories like what are the consequences of Kimball locking, like some, I think there are even accidents and so on and so forth, which you can take a look at from the YouTube channel, which I'm about to tell you. So, Euler angles. Are we back to this? Now I need to take a look at phi theta psi. Okay, good. I'm good. So, Euler angles. The first important thing about Euler angles is what is important to know is the fact that it's based on 3 successive rotation, meaning that once rotating system will be rotated second time. 2 times rotated system will be rotated third time. That's what the successive rotations is standing for. Okay, how it goes then? It goes such that we're going to introduce 2 coordinate systems that are initially parallel with respect to each other. What is this? So it says that I should move on to team system, which I cannot do because I'm middle of the explanation. So we have 2 coordinate systems parallel to each other, and then we're going to take a hold of the one coordinate system in axis Z. We're going to rotate the axis Z amount of that is phi. Look at that. Listen to me. So I know what it is. This is phi. How do I know it? Because I'm taking a look at the chat window, which is, the way to know this. And then I have a coordinate system that is once rotated. Then I'm going to take a hold of the once rotated coordinate system, and I'm going to introduce another rotation around the axis X. This time the axis amount of rotation is theta, and I'm going to have a coordinate system that is 2 times rotated. Finally, I'm going to take a hold of 2 times rotated z-axis. I'm going to introduce the rotation, that is the amount of rotation is c, this guy here. Now these are my 3 successive rotations, and as you can see, the order of rotation is x, z, x, which is very commonly used. I've been thinking like why it is so commonly used, and I think it may be because of the gyro, because in gyro the axes are exactly that way. Excuse me, I put that wrong. This z, look at that, z, x, z. That is a sequence. So z here, x then, and again z. And as you know, you can put the gyro to any orientation in the space, so this should work. It will work. Okay, so what it means mathematically. Mathematically, we can describe these rotations by using 3 by 3 rotation matrix. And look at this telling where the rotation axis takes place. First one is obviously z, second x, and then z again. And the final orientation, I can find it out by multiplying these matrices together. So all these matrices together, and this is how it looks. So this is my 3 by 3 rotation matrix. 3 rows, 3 columns. That is mapping my description from one coordinate system to another, from body to global, if that's what you wanted to do. And it is based on 3 parameters, which is called Euler angles. And again, these parameters are phi, theta, and c. And they're standing for those rotations that we described earlier. Okay, so that is a method. That's the one method that could be used. It's easy to use because these angles, they have a clear physical interpretation. So it's easy to understand what is that they're standing for. Okay. Now, this was already mentioned. Those are this axis, so this sequence of rotation is all very often used. It could be something else. It doesn't make any difference really. For drawbacks and advantages of the method. So it's still going to be the same. Now, what is the most serious and most severe drawbacks of these Euler angles? And it is singularity. Now, there's several different YouTube sites which you cannot really copy here. So what I'm going to do is that I'm going to place those links to Moodle site, so you can just click these links and you can learn like what these singularities means and how is that you can handle those singularities. Now, basically the singularities means that that if the first rotation here, just to give you an example, is 0 or phi, then you can really differentiate the first and third rotation. So it's going to be kind of like having the same rotation axis. And this is something that is called gimbal locking. So the gimbal locking is not a mechanical lock, but it's an inability to describe certain rotation because the system goes in a configuration that they cannot differentiate the 2 rotation anymore. That's what the gimbal locking is actually about. Numerically, there are many different ways to avoid the gimbal locking. You can add some artificial rotation to your system. You can deal that in many different ways. You can actually monitor the rank of your rotation matrix, and you can recognize that when is that you started to face some difficulties. But when you have an apparatus that is measuring angles like a gyro, this can go to the configuration. This can go to configuration that these 2 axes are parallel, so making it kind of impossible, making it not possible to see how the system is having the full orientation. So that's what is called gimbal locking. There are some good stories about how the gimbal locking takes place. And again, these are the videos that I'm not going to play to you today because I'm not sure if in a one YouTube channel you can play other people's YouTube videos. Do you know that? I don't know. But I just want to play safe because I don't want anyone to complain. So I'm just telling that these are the links that I'm recommending you to look at. So please take a look. This particular is really good. I don't know, maybe should I just play this because this tells about the gimbal locking in a really clear way. Let me first hear if this goes out.
Those who followed my Apollo 13 live stream probably saw the phrase
no,
gimbal lock pop up a number of times, and a lot of you asked me what it is. So today on Vintage Space, we're looking at what exactly is gimbal.
Is it going out, or can you guys hear that lady to talk, or you are unable to hear it? I guess that I should do a little bit of tuning to make that something you can hear it. Oh, you can hear it. Okay, so let's look at this. So because you know, you can see that we're kind of running out of the time, and we can only open shortly this topic of friend request equation, but no way to complete it. Gimbal lock. Let's learn this together.
So we need to break this one down just a little bit before getting into the question of gimbal lock. At the heart of the Apollo guidance computer was an inertial measurement unit, or IMU. The IMU is a spherical housing about the size of a soccer ball that contains 3 nested gimbals. They're set at right angles from one another, supporting a central platform mounted on the innermost gimbal. The outer gimbal is mounted on the navigation base, and this is mounted rigidly to the spacecraft. Every time the spacecraft moves, or rather every time the IMU detects any kind of change of attitude, the gyros signal to motors to return the platform to its original orientation. So as the spacecraft moves around on its path to the moon, the guidance platform inside remains stable. The guidance platform was aligned on the ground before the flight, and of course it would drift occasionally during the mission. To compensate for this drift, astronauts would realign the platform using star sightings, but its use still remained, and it still gave the astronauts information on their attitude in space. The information from these gyros was displayed on the Flight Director Attitude Indicator, more commonly known as the 8-ball. So it's the fact that there are 3 gyros involved in the IMU that make gimbal lock possible. The 3 gimbals account for the spacecraft's 3 axes of motion, its axes of pitch, yaw, and roll. Because the IMU works in all 3 directions,
so different order of rotation that I explained to you, that makes no difference. The gimbal locking is still possible.
Any change in the attitude's orientation at all is registered on the 8-ball. The constant attitude information about these 3 axes gives the astronaut a very keen sense of exactly where they're pointing in space, but it's also something that you can lose. The phenomenon of gimbal lock is one wherein the outer gimbal moves with the spacecraft to a point where it lies parallel to the inner gimbal. At this point, all 3 gimbal axes
Parallel. So that's the keyword.
Would be lined up on a single plane, and none would be able to move around the basic plane to resume a normal orientation. In short, once the gimbals are lined up, they can't realign themselves to give you an orientation, and they become locked. It's the confluence of 3 angles.
Not mechanically locked. No one gonna go and welded them together, but it's again inability to see how the orientation is because they are having the same axis. That's what it is.
Angles of the gimbals that creates gimbal lock and prevents them from moving around to get out of that situation. The Apollo guidance computer was actually designed to prevent gimbal lock by giving the astronauts a warning when they approached that devastating alignment. However, it was possible still to fall into gimbal lock. This was what was happening on Apollo 13 when the spacecraft was wildly pitching and yawing around in the wake of the oxygen tank.
Look at that. I wasn't, Apollo 13. That's a new information to me too. So maybe I wasn't really watching this carefully enough. Okay, let's hear the rest of the story.
Explosion. And that is why you hear in the movie and read in the transcript astronauts yelling about watching the gimbals. Losing their attitude in space would have made the entire situation on Apollo 13 just that much worse. The simplest way to avoid gimbal lock would have been to add a 4th gimbal into the IMU, just giving it another reference point so that the 4 wouldn't be able to align the same way. This is what Mike Collins actually asked for Christmas, jokingly, when he was orbiting the moon on Apollo 11. From his orbital vantage point in the command module, Collins was trying to find the lunar module Eagle on the surface, but every time he got close to gimbal lock, he had to stop. And that's why he wished he'd had a 4th gimbal on board. So I hope that clears up gimbal lock for you guys. If not, leave a question below and I'll try my best to answer it. But I also want to give you 2 quick book recommendations of things that would maybe explain it in a lot more detail. The first is Frank O'Brien's The Apollo Guidance Computer, which is everything you ever/never wanted to know about the Apollo Guidance Computer, and it is a brilliant resource. And the second is How Apollo Flew to the Moon by Dave Woods. It is It is exactly what the title says. It is the details of how Apollo flew to the moon, including the guidance computer. Both are fantastic resources by excellent authors, and I would highly recommend it if you guys want all the nitty-gritty details on things like attitude control in space on Apollo. So as always, leave any questions, comments, and ideas for things you'd like to see covered in future episodes in the comment section below. Be sure to follow me on Twitter for vintage space content every single day of the week. And with new episodes going up every Tuesday and Friday, be sure to subscribe right here so you never miss an episode.
Great. So, with that, let's move on. And let me ask you, because I know that I'm really late today, so I only have one in-class quiz today, which is this one. When using 3 rotational parameters, the problem is singularity, physical interpretation of parameters. The usage of 3 parameters is limited to small rotations only. And let me, hold on, let me see if this keyboard works. So it works. So let me log myself to Socrative so you can enter the system. And I can see that maybe you were unable to log in the system because the squeeze was not on. So let me just ensure that the room is on. It is on. So you're supposed to be able to log into a room called LUT. This room, LUT room. And I'm going to put the squeeze on momentarily. Launch here. So it's on. Let me see. No, I still have a wrong room here. So I want to use this room. Okay, I see that we have 17 students. So maybe you cannot see the in-class quiz yet. Here. Okay, so it's on. I see I have 19 students that are in Socrative. Let me just share that with you. Oh, I guess that I need to make this a bit smaller, like this. Okay, let's put it here. And let me see how many students I have in the stream. So we'll still need to relocate that a little bit. So let's not go there yet. Let me see. I have 29. I guess I have 29 students in this screen here. I suppose so. So, and how many answers? I have 9 answers so far. And I can see, let me take a look at another thing that I could possibly see here, like how many students are in the Socrative system. So just a second. You know what makes me really, really happy? 22. Awesome. So I'm expecting to get at least 22 answers here. You know what I've been, okay. Where can I find a student ID to log in? Okay, that I don't know. I suppose you have a student ID number. So I guess if you log into Moodle site, can you see your student ID number in Moodle? That's something that okay, that's a good explanation in Sisu. So you can log into sisu.lut.fi, and then that's the way to see your student ID number. I really don't know much of the details on Sisu, so I cannot really help you where exactly you can find it. Okay. Okay, and those ones that are, another good hint is that if you're unable to log in, you can just forget about the 0 in the beginning of your student ID number, because this system, Socrates system, is not accounting zeros. So I have 20 students, and let me see how many, 22 in the system, so I'm expecting 21 answers. So if I'm gonna get one more answer, then I'm gonna solve the result. So if we're gonna get 100% success rate in the beginning, that will be, I don't know, that will be such a great start for the course that I don't know what to say. Would make me, okay, I got 22 answers, so that would make extremely happy. Me is extremely happy. Okay, ready? Okay, so game is on. So the game, you know, what the others are doing, they're guessing what is the success rate. So you can guess the success rate, and if you hit it correctly, this is lottery, you can get one additional point. So we got the answers from, I mean, guesses, not the answers, but guesses 75, 98, 96, 86, 84, 85. You know, would you like to learn my personal guess? My personal guess is this. I am using chat window. Yes, 100%. What are these numbers? Why you guys are guessing that is this slow? Like 80, 60. Oh, come on. It's higher than that. 55. Statistically, it's going to be 30, 34. But I think it is going to be 100%. No one is guessing 100%, so no one is with me. Okay. All right, I know that I'm spending a bit more time than I expected, so I'm going to close the case momentarily, and we'll see if we're going to get the winner here. So we got 23 answers, and if you missed today's in-class quiz, that's going to be fine, because there's going to be plenty of in-class quiz in the row. Okay, 96, I like that. Okay, the results are this. Oh, let me just check one more time how many students I have in the system. 24. Oh, look at that. Because, you know, it came with a certain delay. I thought that it's going to be 100% success rate. I thought that it's happening already in the first in-class quiz. Wasn't the case. But we got 88. So let me see if we got somebody that won in this lottery. 86. So 86. Do you guys think that the 86 is close enough? 85, 87. I think that is a winner. So I think we have one winner. That's 87. All right. So let me put that to my notes. Winner list. And with that, I'm going to close today's lecture, and I'm going to see you on Wednesday with more in-class quizzes, more things to discuss. So, here's my winner. So I'm going to close the recording. So see you momentarily in Teams, so we can discuss some more in Teams. Thank you, and take it easy.